Formula One, the world's largest annual sporting event with a television audience of 1 billion watching 19 races live, taking place on 4 separate continents. It's a world about speed, not only on the racetrack but in the factory, where a virtual race takes place every day. Performance in Formula One is determined by 4 key parameters: drivers, engines, tyres and aerodynamics. In terms of drivers, you've got to have the best. Engines can't be touched, as we're in a world of frozen engines, and tyres are the same for everyone. So that's why the Renault F1 team places so much emphasis on aerodynamics, using the wind tunnel to create downforce and minimise drag. But for the aerodynamic designers, times are changing, and the future is all about computational fluid dynamics, a tool that is revolutionising the design process of Formula One cars.
This is a big step. It's an astronomical step for Renault team for the future, this is sure.
Basically, it's a virtual wind tunnel taking place in a supercomputer, a technology enjoying a rapid growth thanks to the development of computational capacity.
These techniques represent the future, and it's an attractive proposition for potential commercial partners and technical partners to come on board and work with us for the future.
C'est un outil au service de l'équipe, du team ici. C'est un outil qui doit contribuer à l'amélioration de la performance de la voiture. Et je pense que c'est un outil dont nous sommes fiers et nous attendons maintenant les résultats sur la piste.
In 2007, the Renault F1 team decided to create the CFD Centre, starting a race against the clock. ABM was chosen to implement the construction of the building, which took 267 days from enabling work to practical completion, with constant attention paid to planning and environmental concerns.
There was 2 reasons that we've put the building underground, really. One, it's a contribution to a green effect. Obviously, a building underground maintains a very stable temperature. Secondly, we have constraints on planning requirements in this area because we are in the middle of the countryside. So we've decided, based on those 2 things, to actually dig out a very large hole, maintaining all the soil on site, which obviously saves a huge amount of movement of vehicles to take it away from site, and put the structure underground. And we've looked towards this curved concrete precast structure to achieve the results for that.
The local authority are very interested in promoting new buildings that are demonstrating clear environmental sympathies, and so we conceived a building that was underground, it's low level, very little visual impact on the local countryside, and then it benefits from environmental issues because it's underground. It's very easy to control the temperature, it's very energy efficient, and we think that's a good statement that the company is making for the future.
24,000 cubic metres of material was quarried and maintained on site to enclose the 25 sections of modular concrete block surrounded with a damp-proof membrane. This ultimate aerodynamic laboratory is now hidden 1.5 metres below the ground. Reminiscent of a James Bond movie set, the CFD Centre welcomes its engineers into an exhibition hall. To the left are the CFD research offices. To the right is the auditorium where aerodynamicists can discuss, visualize and share ideas about the results of their simulations. Thanks to the latest technology supplied by Bose and Barco systems, they can display their results from a full-scale 3D car model. One-third of the building is dedicated to Mistral, the supercomputer. Named after a southern French wind, this is the brain of the facility where all the number crunching takes place. Measuring some 52 metres end-to-end and weighing in excess of 10 tonnes, the supercomputer, supplied by APRO, is actually 500 computer servers running together as one. Capable of performing 38 trillion mathematical calculations per second, the supercomputer can store the equivalent of a DVD worth of data every second.
They need more and more power because they need to simulate the airflow around the car as accurately as they can, as the technology can help them. They need to do that all the time and 24/7. So the more engineers and the more power capacity we've got, in this big computer, the more performance we can add on the car.
Although CFD technology can also be applied to such areas as modelling gas flow through the exhausts or simulating combustion within the engine, the CFD centre is mainly about aerodynamics and how the car manages airflow around its surface.
It's absolutely essential to have a very large computer to do this work. What it basically boils down to is you take the air around the car and you divide it up into lots and lots of tiny, tiny little blocks, and you analyse all of the flow conditions in each of those blocks simultaneously. And the accuracy of the solution depends upon the number of those little blocks. The smaller you make them, the more of them, the more accurate the answer. And that means you need a bigger and bigger, faster and faster computer.
The decision to head towards a wind tunnel in a computer rather than constructing an expensive second wind tunnel is down to the team's strategic approach.
I think it was a fairly clear-cut decision for us. It was a decision based on, first and foremost, technical belief that this was the way of the future. And it was also based on sound, pragmatic commercial judgment. This facility has cost us less than an equivalent wind tunnel capacity would be. And it's also a facility that is of interest to potential partners and sponsors. It's new, it's ultra-modern. Wind tunnels are old-fashioned. They're commonplace almost, and there isn't a lot of development there.
A wind tunnel is very good at being able to run through a significant number of different configurations very quickly. The problem is that although you find out whether or not the part has worked, it's very difficult to really get an understanding of why it is better or why it is worse than the other part. In CFD, the process is slightly slower because the modelling is more difficult, but the ultimate result you get gives you a much better understanding of why the part is actually better or worse. So really, the two technologies complement each other and don't compete with each other.
In 2008, we signed a 3-year partnership with CD-adapco. And as part of this partnership, we can work a lot more closely with CD-adapco. We've got access to a lot of their expertise. CCM Plus. It's a state-of-the-art CFD code that's relatively new. The code itself is fast, it's robust, and it's extremely easy to use.
The software can be developed and improved over time to give more and more capability to what we're trying to do. That's not possible with a physical wind tunnel. They've reached the limits of their performance development.
The creation of the team's Computational Aerodynamics Research Centre also heralds a new era for the Renault F1 team's collaboration with Boeing company's Phantom Works. By working together, both organisations have developed highly specialised CFD tools that offer a quantum leap forward in computational capacity. This will benefit not just the team and Boeing, but the Renault-Nissan alliance and, indirectly, society at large. The choice to invest in this technology will also open the doors on the future for the Renault F1 team as it continues its never-ending quest for speed.